Hey Radical Scientists, this is Mr. Giovanni with another series of problem walkthrough videos as we wrap up not only this unit on forces in motion, but also our year of learning here as a community. Now, as we are wrapping up things, as we are looking at some of the last problems and preparing for our one and only practice, our one and only test, I wanted to be really explicit about the intentionality that I've had as we are looking at more and more math at the end of the day in this unit. On one hand, I do want us to get that preparation for how physics will normally be assessed in spaces outside of our classroom, but to be also transparent, I also have this goal in mind about not only being able to learn how to solve specific problems like we've been doing all year with these videos, but to also support the development of a problem solving strategy that will really center the learning process as a whole. I will be trying to be clear about what type of process that I'm trying to support in some of these example problems, but at the end of the day, what I'm really trying to I think convey is that while it can be pretty overwhelming to look at a lot of physics problems, for example, at a time and be like, I have to learn how to kind of do this problem in this specific way, truly, I ask us to truly take a moment to think about how math can be a tool that at the end of the day we can use to manipulate, right? Different situations with different little variables or circumstances allow us to really think about what is in our current situation and how do we actually use those tools to apply it. And in this case, I hope that we can develop a type of confidence where we're not looking at these problems and feeling overwhelmed about how much do we know, how much will we get done, and just thinking of each problem as an opportunity to test the actual skill of translating, applying some type of equation, and ultimately solving for what we're looking for. If you watched the first video of this series, you will have already heard these words, but otherwise, folks, here is our second problem for practice. And here we go with our second practice problem. Once again, I'm putting the assignment from which this problem is coming from for your own understanding to know what kind of type of problem this is. But once again, let's try to just solve it without the context to test how we can basically translate from any problem to an equation that we have to use. A car slams the brakes after a dog runs to the road. If the car is traveling at 10 meters per second before applying the brakes and decelerates at -5 meters per second squared, how long does it take before the car stops completely? Once again, the two questions that we ask ourselves to start us off. What are we looking for? In this case, once again, we are looking for something that might be asked in that last equation, right? How long does it take before the car stops completely? How long does it take seems to be the question in mind, right? And in this case, that long is referring to a distance or a time. How long does it take before the car stops completely? I'm going to assume here that it's talking about some type of time, only because how long is it doesn't seem to, that would be like a better way to ask for a distance. So I'm going to go ahead and write time as our final destination, right? We don't know what it is. We know that's going to be an unknown, but we're going to use stuff that we know in order to get to that solution. And this leads us to our second question. What do we know? Car slams the brakes. If the car is traveling at 10 meters per second, I'm going to go ahead and bring some attention to those numbers. As always, 10 meters per second is some type of velocity. V is equal to 10 meters per second, some type of velocity. We have here a unit of meters per second squared. That tells me it's some type of acceleration. So I'm going to go ahead and write that as our acceleration here. And read a little more closely for any other values. If the car is traveling at 10 meters per second before applying the brakes, so the brakes are -5 meters per second squared. How long does it take before the car stops completely? Here we see once again this word stops, right, which tells us that it does have another velocity in mind there. This was before the brakes were applying. This is afterwards. There is some type of 0 meter per second velocity. That's how we know something has stopped. It is still and it is no longer moving. So with this in mind, a T, V, I, A, D, F, we can once again reference our equation sheet, some notes that we might have, right, to find the VI, VF, acceleration and time. VI, VF, acceleration and time seem to still be in this one equation here. And we're gonna apply, and so it sounds like this is the equation in mind, right, that might be relevant. So once again, there is a VF there, there's a VI, there's an acceleration, and there's a time involved. It looks like we have everything we need, including what we don't know, right, all related. That's the important part. I'm gonna go ahead and start plugging some of the numbers in. 0 meters per second is equal to an initial 10 meters per second plus an acceleration of -5 meters per second squared, all or that multiplied by our time missing. Now, with this in mind, I see that this t and this acceleration multiplied is related with addition to this velocity. So I'm once again going to be subtracting by that 10 in order to get a 0, something where we're only focusing on what's being multiplied. This on the left side, right, because we're subtracting and to undo an addition, means that we're going to be left with a negative 10 meters per second on the left side. You have a -5 meters per second squared multiplied by our time, and this seems to be a multiplication relation. We're going to do that with a division, and in this case again, because it's being divided and not added or subtracted, we keep that negative in order to undo what is there, which is a -5 meters per second squared. -5 meters per second squared over here gives us here a 1, right, which just leaves us with a t on the right side. But here it's a little more complicated. Well, we know that the negative and negative will cancel out to a positive. 10 divided by 5 should just be 2. What about our units? We know that these are two numerators. They're being divided, so that cancels out. Seconds squared is a little more difficult to map out. But if you can imagine that this denominator and this denominator cancels out, there's another second in the denominator. We're basically going to be left with 1 over a 1 over second. This translates into 1 times, if we multiply by the reciprocal, s over 1 gives us a unit ultimately of seconds. It's all a long way to say that these units map out perfectly with 2 seconds as the last unit for our solution. At the end of all of this relation in math, we can name 2 seconds as the time it took for this car to decelerate completely.